Okay, I'm back. All right. So now that first little bit was about what the units of the integrals would be. Okay. Hopefully not too complicated, but that's just the idea. So we want to, whenever we solve an integral like an application problem like we're going to do, we want to be able to say what the units are and what kind of, what the answer applies to. When we take an integral, what exactly are we calculating? Okay. So here though is we're going to get at now the fundamental theorem of calculus, okay? And now that sounds pretty grand, doesn't it? But it's important because it's along with the definition of the integral, the definition of the derivative, which led us to all kinds of derivative formulas and derivative applications. This same thing is the same way the doorway to integral formulas and integral applications that we have to get at first. But first we have to understand what's going on with the fundamental theorem of calculus, and in the same way, first we're going to make sure we understand sort of intuitively and visually what the fundamental theorem means, and we'd be able to apply that, including being able to describe what the units are. Then, after that, you start getting at, like we did with derivatives, after that you start getting at what some of the specific formulas and procedures are for actually calculating an integral, and then after that we do some applications, okay? All right, although that will probably be on what we're going to be able to do in this course, okay? All right, so at least the applications part. Okay, so the fundamental theorem of calculus. So so I want you to consider this situation here, okay? And remember what we're doing is we're finding the area under the curve, right? Which tells us, and remember what the area under the curve, what that does for us is it allows us to add things up, to find totals. For example, in the case that we've been working with mostly so far is, if we know the speed of the vehicle and we know the time for which it's traveled, finding the area under the curve allows us to calculate the total distance that it's traveled. Okay? It also is another way to find averages, for instance, but we'll get to that later on. Okay? So far so good? Okay. So the way we're going to get at that is to start with is we can recognize there are certain situations besides rectangles in which we can calculate an exact area. So let's say, for instance, we've got this situation here where we've got, and I'm not going to call it speed or time or distance, I'm just going to say we have this function f of x equals 3x, which is that straight line going up, right? And here's f of x over here, which are the y values, and here's x down here, which are the x values, right? Obviously. Now we want to be able to calculate what the area under the curve would be, what a formula would be. If we know that this is f of x equals to 3x, what would be a formula to calculate the area under the curve? And that area under the curve, you understand, let me make that a little bit more clear here. We're going to call that capital F of x. So if the equation of the line or the curve on top is little f, 3x, the area from 0 up to any arbitrary value x, we're just going to call that some value f of x. So what's a formula? We want to get at a formula. If we know 3x, what would this be? Okay? Well, as it turns out, because that's a straight line, as you can see, that's a triangle. And we know how to find the area of a triangle. It's base times height divided by 2, right? So in terms of this picture here, what's the base? Well, the base is from 0 to x. So the base is equal to whatever x is, right? And then the height as you can see, so the base here is x. The height, as you can see, is whatever f of x is. So it's x times f of x, and then divided by 2, yeah? Okay, well, so for this specific particular curve, if this is x, what's f of x going to be? Well, f of x for any given x, f of x is going to be equal to 3x. So I'm going to write it up here. F of x, you understand, is equal to x times 3x divided by 2. Simplified a little bit. That's 3x squared over 2. So, in other words, if the equation of this curve on the top is 3x, the area under the curve for any given x value is 3x squared. Well, ladies and gentlemen, what do these two have to do with each other? Well, and this is super important here, if little f of x is equal to 3x, can you see that the derivative of capital F, if you take the derivative of 3x squared, you get 3x. So little f is equal to f of x. That's equal to f primed of x. Okay? So we see here where f is equal to 3x squared. So here is a stupendous notion. Besides the area under the curve is just length times width. The area under the curve is this rectangle thing. If we don't want to spend the rest of our lives adding up rectangles, how do we actually get at that area under the curve? Oh, if we know this, then we can take the antiderivative to get to this. Because if we'd started out knowing 3x, we could use that handy-dandy little antiderivative formula that we talked about before to get to f primed. So in other words, f of x, oops, it's not exactly the way I want to do it. F of x evaluated from from 0 out to x is going to be this definite integral of 3x times dx. Okay? Very important. Okay, so let's try a slightly more sophisticated example to get a kind of a broader general statement for the fundamental theorem, because we're not quite there yet. All we know right now is that this area here, the area function capital F, is the antiderivative of whatever the equation on the top is. And we picked an easy area here, a triangle, but, you know, let's try something a little bit more sophisticated. Let's say instead of from 0 to x, let's say just two arbitrary boundaries, a to b, like I've got, you know, like we've been doing. What's the area from any two values a to b? Well, you see here, and this is going to be a little bit more algebra, but maybe you can see that now we've got a shape that's called a trapezoid, right? And these are the two parallel sides, what we called in the world of trapezoids, base 1 and base 2. And then that perpendicular distance between them we called the height. And so here was the area of a trapezoid, base 1 plus base 2 times the height divided by 2. Maybe you had that way back in geometry or someplace, right? So that would give us the red area, which would still be capital F, right? Well, the equation up on top, that graph up on top, is still f of x equals 3x. So let's do the same thing we just did here. We have to move things around a little bit, okay? But let's see where that gets us to, okay? So first off, maybe you can see here that the height, the so-called, I'm going to turn it like this, the height of our trapezoid is, I'll put it over here in green. The height would be equal to whatever b is minus whatever a is, right? Would be b minus a. We could call that delta x or something, but let's just call it b minus a for right now. Now, can you see that over here, this is f of b, and this is f of a, oopsie, a, right? Those are the corresponding y values. So base 1, I'm going to turn it like this. This base is however long f of a is, and this base is however long f of b is, right? So we get, substituting in here, so b1, that's going to be f of a, and then b2, that's going to be f of b. Now, f, of course, is 3x, right? So really, this is, I'm going to write it down here. I'll write it like this. This is, using our formula here, the height, remember, is b minus a. So I'm going to put b minus a right there, times. And then this is f of a, which is actually 3a, and f of b, which is 3b, because that's what the f function is, it's 3x. So this is going to be, let's call it 3a plus 3b, and then still all divided by 2, yeah? Okay, good. So now we're going to do, now you're going, oh, Mr. Waters, algebra. That's right, okay? So we're going to do the algebra. Now in order to simplify that, we're going to FOIL that all together. Can you see that's going to be, you know, first outside, inside, last. That's going to be 3ab, right, plus 3b squared minus 3a squared minus 3ab again, all that divided by 2. So far, so good? Cool. Now, maybe you can see, oh, look, the 3ab and the minus 3ab cancel out. And what have we got? This is f, remember. This is the area under the curve. That's the red area there. Maybe I should be using f there so we can remember, I mean red, so we can remember, right? That cancels and that cancels, and we've got 3b squared minus 3a squared divided by 2, right? So, going on to the next page here, or actually I'm going to move it, I'll move it down here a little bit. I'll go over here so we can kind of get it all on the first page here. Separating these into two pieces, if I want to know the area from B to A, or actually, oh, I wrote that backwards, from A to B, from A up to B, I'm going to do 3b squared over 2 minus 3a squared over 2. There we go, sorry. If I want to know the area f from A to B, I'm going to do 3b squared over 2 over minus 3a squared over 2. Well, there's the antiderivative again, isn't it, right? So in other words, what we're going to do here is we're going to take the antiderivative of 3x, which is 3x squared over 2, minus the value of the antiderivative at a, and just subtract the 2. That's the fundamental theorem of calculus right there, which you've got in your book in all its raging glory on page 256. I'm going to write it out fair and square, use in terms of x's and t's and stuff, but that's the idea. If I want to know the area here, I take the antiderivative of 3x, which is 3x squared over 2, and I evaluate it at b. I take the antiderivative of 3x, which is 3x squared still, and I evaluate it at a, and I simply subtract the 2. And that gives us the total area under the curve. Now that allows us, hopefully you can see how that works there, that allows us to do a stunning number of problems, right? and it shows that the area under the curve is calculated by working whatever the antiderivative of whatever the curve is. So this doesn't have to be 3x, you understand. It could be cosine. It could be 2 to the x. It could be a log function. It could be any stinking function you want, okay? Because it's still going to be antiderivative of b minus antiderivative of a. That's the fundamental theorem of calculus. Okay, so I'm going to put that aside here, okay? And we're actually going to write it out fair and square, okay? Fundamental theorem of calculus. Ooh, we're coming back to that now. And it goes like this, that if you've got some function f of t, and I'm going to switch to t here instead of x because it's this, it doesn't matter what the name of the variable is, and they tend to use t in the book because we're still thinking about time and distance. And we happen to know that f of t is equal to f primed of t, right? Where f of t, where capital F is the antiderivative of f. In other words, if we start with capital F, the function, and we take the derivative, we would give us f. This is the fundamental theorem right here. Okay, it's what we just did with the trapezoid, and actually also with the rectangle, also with the triangle, but in the case of the triangle, a was equal to 0, so f of a was equal to 0, okay? So we just ended up with what f of b was. Okay, so notice that we still have here the idea that we're finding areas, right? Length times width, if it's a rectangle, right? So we're still finding area. Fundamentally, that's what that says. It's just that our little strips, we're still adding up little rectangles to get that area. But how do we actually do it if we're not going to spend the rest of our lives adding up rectangles? We do it like this. We start with f. We find the antiderivative, whatever it might be, using formulas or whatever other process, right? And then we evaluate b, f of whatever that bigger function is, and f, remember, that represents the area under the curve. That's the function. That's the f is the area under the curve, right? Minus f of a, capital F of a. Okay? Now, so that's kind of how, that's our derivation for the fundamental theorem of calculus. And then later on, we will learn some formulas for it, okay? To actually calculate the antiderivatives. But for now, like we did with derivatives, we're going to focus on what does it all mean. And actually, this antiderivative, this calculation right here, at first, we're just going to let our calculators do it. And I showed you sort of briefly last time how we find antiderivatives and integrals on the calculator, but we'll go over that again today in a minute. Okay, so the last little bit that I want to get for this video is there's another way to look at this derivation, okay, and that's this. So going back to the trapezoid that we just had, okay, okay, so here is our f of x, and I'm not even going to give you make up a specific equation for that because it really don't matter. Okay, so let's say we want to think about the area under this curve from A to B. Now what we've been doing is we've been dividing it up into rectangles, right? And as you see here, since this was what we call the left side sum, or the left-hand sum, which in this case would give us an underestimate, but that doesn't matter, right? Because, you know, we imagined through our limiting process that delta t would get closer and closer. With delta t here, we'd have more and more and more and more and more triangles, right? We'd let the number of more and more and more rectangles, and we let the number of rectangles go to infinity. Can't really go to infinity because that's not a number, but we understand that what we mean by a more and more and more, 1,000, a million, a billion, a trillion, that makes delta t smaller and smaller and smaller and smaller, and it made each of these areas, each of these rectangles more and more and more thin, right? And it didn't, in the end, it didn't matter whether you were using the right-hand sum or the left-hand sum. They both, as it got thinner and thinner and thinner, they trended towards each other with the actual area in the middle. And so if we imagined that through that limit as x goes to, as the number of rectangles goes to infinity, that would represent the actual exact area under the curve, right? So you can see here, so here is f of x, right? So here's another way to think about the fundamental theorem here, okay, is that's from A to B, right? Okay, and then so this was, if you remember, calculus is changing and increasing. So as we go from A to B, imagine that this area is increasing, that there's a point here, x, that's going from A over to B, and it's slowly opening like a curtain or something opening, right? And it's slowly opening, and it's opening and opening and opening, and this area is getting bigger and bigger and bigger. Well, that is the rate at which that function is changing. The rate at which that area is increasing is delta f, right? And so each of these rectangles represent an increase in the area of the function as A increases, as our area increases from a low of A up to the highest value B. So each one of those rectangles represents delta f, right? So that is the area of that rectangle is delta f. So for this one, so that would be delta f would be the area of that rectangle for delta t1. So let's call that delta f1. And the height of the rectangle, as usual, was f1, let's call it, right? Whatever, that interval limit there is 1. Okay, then this was f2. Little f2 was the height of that rectangle there at 2. And then, so this is area 2, that's 2, this is delta t2, right? And then this is going to be delta f3. That's, again, as we're increasing here, this is going from left to right, and so this is another increase, another change in the area, another increase in the area that we're going to call delta f3. Well, this is the corresponding increase in t is delta t3, and this is the corresponding height of that curve on the top, little f, is that's f3, right? So this area, you understand, was, so the total area here, you understand, would be delta f1 plus delta f2 plus delta f3, right? Well, what's that equal to? Well, that's equal to f1 delta t1, f2 delta t2, f3 delta t3, right? So the increase in the area, well, the total area, f, would be all three of those added together, right? So in other words, f1 delta t1 plus f2 delta t2 plus f3 delta t3. And if this looks like just what we were doing before, you're right. It's just another way of looking at it. So this area function, so that area worked out to be, imagine delta t gets smaller and smaller and smaller and smaller, right? Well, for the left-hand area was, yeah, n minus 1. F1 Fi delta t I, right? And if we let n go to infinity, through our limiting process, f was equal to, for whatever a to b is, f of x dx. So remember, don't lose track. Just like we didn't want to lose track when we did derivatives, that was a rate of change. It was the change in y over the change in x. The integral is x times y, right? That's how we got the units in the beginning. So that shows us this area here. Okay, so that's how that goes. So this is the fundamental theorem here. This is when you're doing integrals and you're using them to solve problems, this is what you're doing right here. This process here. Now, this is 26 minutes in, so I'm going to end this video right now, okay? And then the next one, I'm going to take up and we'll do some applications of this fundamental theorem using, again, this our rectangle method, our Riemann sum method that we've been working with, okay? Bye.